So, good evening, everyone. Today we'll be doing our 12th lecture of the course Introduction to Commutative Algebra and Algebraic Geometry, and this will be our last tutorial as well. So, in this week, Professor Dilip Patil will introduce to you integral dependence and integral extension and everything, and some properties of that. So we will be doing some assignment problem based on that. So here is your exercise 1. So let f a to b be an integral homomorphism of rings so that f alpha star spec b to spec a is a closed mapping. This property is called normalization, and you know that integral like integral extension is same thing as finitely generated module, that is a finite map. So yeah, closed mapping, that is it maps closed sets to closed sets. So we'll start solving this problem. Now so we'll start with a definition. Integral homomorphism if a to b is a ring homomorphism such that b is integral over f. Then we call a homomorphism is an integral homomorphism. Now we can factor through f as a going to f of capital A to capital B via say two maps R and S. Then R is a surjection and S is an injection. So from a previous result we know that R upper star is homeomorphism of spec capital A onto V of car R. You remember that I did this proof while doing Jariski topology in that lecture, or you can just simply reference to this exercises Atia McDonald exercise 1.21 V4. Thus you can say that it is a closed map. So it suffices to show that S upper star is a closed map. Let small b be an ideal in B, then B intersection F of capital A is a contraction of B with respect to I. It suffices to show that S upper star V of capital B equals to V of B intersection F of A. Let P be a prime ideal in spec of F of A containing B of F of A. P bar is prime ideal over F of A by B of F of A. So from Atia McDonald proposition 5.6, proposition 5.6 Atia McDonald, B of Gothic B is integral over F of A by of Gothic B intersection F of A. Thus there exists a prime ideal Q bar such that Q bar intersection f of a by b intersection f a, it should be isomorphic to p bar because of this calculation we did. So if we let phi to fa section b fa going to small b is a canonical injective homomorphism then phi upper star is a surjective continuous map, and since spec capital B by Gothic B is isomorphic to V of Gothic B, which is contained in spec of capital B, and we can again, this is a simple observation that spec of F capital A by Gothic B intersection F of capital A is isomorphic to V of B intersection F of capital A, is contained in spec of F capital A. So compiling all these observations, you can see that this follows, where this phi upper star maps to spec of F of capital A by B intersection F of A is isomorphic to V of B intersection F. So is a surjective continuous map. This long map is a restriction of S upper star on V of Gothic B. Thus, S upper star V of Gothic B should be equals to V of B intersection F of A. So we are done. So what we are trying to do is that if f of A to B is an integral homomorphism of rings, then we have to show that F upper star is a closed mapping, and it means closed sets to closed sets. So now we'll be going to our next question, that is exercise 2. Let A be a subring of a ring B such that B is integral over a, and let f of a to omega be a homomorphism of a into an algebraically closed field omega, so that f can be extended to a homomorphism of b into omega. So try to understand this problem, and we'll meet after 5 minutes.
কেউ নেই, দেখতে পাচ্ছিস কেউ নেই?
আমি কিন্তু জয়েন করে দুজন জয়েন করেছিল, ওরা হচ্ছে ইন্সপেক্টর গুলো, মানে ক্লাস নিচ্ছে কিনা ওরা ইন্ডিভিজুয়াল ওরা সব চলে গেছে।
তুই কাকে দিলে দেখতে বলছিস 1 মিনিট?
এইটাই তো, কাউকে না, আমি যাতে উঠে একটু এই যে ফ্রি হতে পারি, ঘুরে দিতে পারি, আবার কমপ্লিট করে বসে মুহূর্তে চলে যাবার মাঝে মাঝে একটু বাদিকে দাঁড়িয়ে থাকি। আমি অ্যাকচুয়ালি লাইব্রেরিতে পড়াই, আজকে কেউ নেই কিন্তু এখানে পড়ি। তো ডিস্টার্ব হচ্ছে না?
না, আমি পালিয়ে যাবো।
ঠিক আছে। Okay, so we shall start solving this. We note that if A is a subring of omega, thus if A is isomorphic to A by kernel of F, and kernel of F is a maximal ideal of A. Say M equals to kernel of F. Then there exists a prime ideal M bar of B such that M bar intersection A equals to M. Hence, B by M bar is integral over Fa. Thus, if we find out an injective homomorphism G bar B by M bar to omega, which is extension of F bar A by M then G of B by is an extension of F since for any A belongs to A, B have G of A equals to G bar Gothic M dashed equals to F bar of plus Gothic M equals to Fa. Thus, just assume that A, B are integral domain. Let epsilon to C, small h, A belongs to C to be H by A if be a set of all pair of integral domains C and an extension of F over C. Define order capital C comma H, then C dashed comma H dashed if C is contained in C dashed and H of H dashed C to H. Then A comma F should belong to capital sorry some sigma, and for any chain the union of all rings in the chain and maps give well defined integral domain and maps into this omega. Thus, by John's lemma, there exists a maximal element capital C comma small h if C doesn't equals to B, then there exists small b from B complement of C. Since B is integral over A, B is integral over capital A. Thus, integral over C. Hence, 0 equals to so 1 to n Ci b to the power I for some Ci of capital C. Suppose that n is minimal among all possible polynomials having C as its 0, then phi of x equals to I equals to n to n h of ci x to the power I omega x also omega x minus phi of x isomorphic to the function field defined by C and omega is a field from the basic fact about field extension. Since is algebraically closed, omega first bracket C should be omega, hence rho from C third bracket x to omega x labeled by h going to omega x by phi of x. So this map is a homomorphism with kernel, you know that summation ci x to the power I. So is a homomorphism map with a kernel summation equals to 1 to n ci x to the power I, and it is extension of h. Thus induce an injection C of third bracket x by xi equals to 1 to n to omega. Since Cx by summation I runs from 1 to n ci x to the power I is isomorphic to C of b as a ring, this induces an injection from Cb to omega extending h. Since Cb is strictly bigger than see it contradicts maximality of C, H. Hence C equals to B, and we are done. This is little long and rigorous proof, but actually this is linear and one can understand if one reads this thoroughly. So now we'll be doing an interesting problem, that is exercise 3, and it is like that. Let A be a subring of B such that B is integral over A. Let ta be a maximal ideal of B, and let M equals to the intersection A be the corresponding maximal ideal of A is Bn necessarily integral over An. So this question is embedded with an example checking. So consider the subring kx square minus 1 of kx, where k is a field, and let equals to x minus 1, the ideal generated by this. Can the element by x plus 1 be integral? So try this for 5 minutes, and then we'll be doing this. Okay. Now, so uh, so we'll answer this question by this example showing that Bn is not necessarily integral over Am. So we'll be doing this by contradiction. So the solution is no. Suppose characteristic is not equals to 2. Let b equals to kx and a equals to kx square minus 1. Then b is integral over a. Since f of y is to y square minus 1 minus of x square minus 1 is a polynomial over a having x as its 0, let 2 equals to x minus 1 be a maximal ideal of B. Now one by x plus 1 is an element of beta since x plus 1 doesn't belongs to eta. If it is integral over Am where to eta intersection A c square minus 1, then j equals to 1 to n aj by sj at x plus 1 intersection j is to 0 for some aj by sj am with an equals to 1 by class নিচ্ছিলে by multiplying x plus 1 on each side of fraction, we can assume that j equals to 1 to n a of j x plus 1 to the power n minus j by sj x to the power 1 for n equals to 0. for different ages. Now, since B is integral domain, a n t n j equals to 1 to n minus 1 aj tj x plus 1 power n minus j equals to 1 to n aj tj x plus 1 minus j equals to 0 in B, where tj equals to I not equals to j sj by multiplying x plus 1 to the power n and I equals to 1 to n j. Since Sj belongs to a minus m and Tj belongs to a minus x square minus 1, thus x plus 1 divides plus 1 divides n minus n, j going to 1 to n minus n, aj tj x plus 1 power n minus j dot. This implies that a n t n belongs to x plus 1 to B, and since we assume that n equals to 1, this implies Tn belongs to x plus 1. Also, since Tn belongs to A and Tn belongs to x plus 1, intersection A x square minus 1, so we have a contradiction. So we have a contradiction since a minus x square minus 1 is multiplicatively closed. Now we'll go to our next problem, that is exercise 4. Let be rings and B is integral over A. If x of A is a unit in B, then it is a unit in A. The Jacobson radical of A is the contraction of Jacobson radical of B. So try this for 5 minutes and then we'll be doing this. So yeah, we should start doing this problem. So solution. Since x inverse belongs to B, then 0 equals to j equals to 1 to n aj x inverse j with aj belongs to a and an equals to 1. Hence, by multiplying to the power n minus 1, we get x inverse plus j equals to 1 to n minus 1 aj n minus 1 j equals to 0. Thus, x inverse is a linear combination of xi over a. Hence, it is in A. Now, for the second part, let max of A be a collection of maximal ideals of A. Then, for any m belongs to all of A, there exists eta spec B such that eta intersection A is M. By corollary 5.8 of Atia MacDonald, eta is also a maximal ideal. Conversely, if eta to maximal ideal of B is a maximal ideal of B, then eta intersection A not equals to A, since 1 is not in eta. Thus, it is proper subideal of A, since eta intersection A equals to eta complement. Therefore, it is maximal. Thus, we can conclude with a claim that is, if A contained in B rings and B is integral over A, then max B and max of A has one correspondence given by extension and contraction. Hence, if we denote RA, RB be the Jacobson radical of A and B respectively, then son of A is to of A and the intersection A intersection beta the max of B intersection A intersection RB. So we are done. Now we will be showing an interesting result that the product of integral algebras are like direct product are integral algebras. So okay, it should be exercise 5. Let B1 to Bn be integral A algebras so that the product is to 1 Vi is an integral A algebra. Okay, so try this for 5 minutes, then again we will be start doing this. So we'll be doing its solution. So let b1 up to small bn belongs to this product to 1 to n bi, then for each bi there exists a monic polynomial f(ix) should be ni equals to j equals to 1 plus 1 aij xj equals to 0, having bi as 0. Thus let fx equals to product of to 1 to n fi of x, then fx is monic and has b1 bn as its solution. Now we can rewrite f equals to j equals to 1 to m aj x to the power j with am equals to 1. Now note that multiplication in this 2n bi is coordinate wise multiplication. Thus we can replace x of fx with b1 to comma bn, then f b1 to bn is to f of b1 comma f of bn, which equals to 0 0 comma up to 0 and 0 0 comma up to 0 is 0 in this product. Thus b1 comma bn is integral over a and was arbitrarily chosen. Thus BI is an integral algebra. So we are done. Now we'll be doing one more problem and then we'll wrap up this session and also wrap up this TA classes. So yeah, exercise 6. Let A be a subring of B. B is a ring of a ring B such that the set B minus A is closed under multiplication. So that A is integrally closed in B. So yeah, try this for 5 minutes and then we'll be starting. So let small b of capital B be an integral element over A, then it has a monic polynomial fx equals to the power n to j equals to 1 to n minus 1 aj x to the power j, such that f of b equals to 0 and aj belongs to A. Since fb is to 0 and a0 belongs to A, bn minus 1 is to a1b belongs to A. Since NSA is multiplicatively closed, either small b belongs to A or bn minus 1, an minus 1, bn minus 2 to a1 belongs to A. If b belongs to A, then we are done. Otherwise, since a1 belongs to A, thus b of bn minus 2 to a2 is to A. Thus either b or bn minus 2 plus dot 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 a2 is to A. Iterating this process, we can arrive that b plus an minus 1 is to A. Thus b belongs to A. So we are done. So I was thinking about doing Noether normalization lemma, but since we haven't been introduced tensor products, I was strange that it was not introduced in the course, but it should have been introduced. But anyway, still the design of this syllabus is very good, and one can say that we have learned a lot during this course, at least was introduced. So yeah, best of luck to the exam and future, and we'll be finishing our course here. Okay, thank you.